Okay, g'day everyone, and welcome to today's webinar. It's Understanding the True Cost of DynamoDB. My name is Tim, and I'll be your host for this session. And alongside me is Guy. Say hi to Guy. He'll be
Hey
driving the
everyone.
second half of this webinar. So if you have any questions, feel free to ask in chat, and Guy or myself we'll try and answer them as we go. But we'll also have some time at the end for some Q&A. So DynamoDB, it's known for its scalability and ease of use, but its cost structure, especially as workloads grow, can catch teams off guard. So today we're going to break all of that down for you. I'm going to assume that most of you are familiar with DynamoDB already, but if you're not, don't stress because we'll also be covering the basics of how DynamoDB charges for its different features. And you might wonder why we're even covering this today, this topic, and that's because we don't actually work for AWS. If you haven't already guessed, we in fact have a competitive product at ScyllaDB. So let's say goodbye to Guy and let me tell you what ScyllaDB is all about before we get into it. Okay, so now we're a database company. ScyllaDB is built from the ground up to take full advantage of modern infrastructure. And unlike legacy databases that struggle to keep up with modern hardware, ScyllaDB is designed to exploit multi-core processors, fast NVMe storage, and high-speed networking. And that helps us deliver predictable performance at scale. It's a t-shirt that I'm wearing right now. And we've been, we're best known for providing ultra low latency for high volume workloads at global scale, something which we'll elaborate on today as a direct comparison to DynamoDB. Now, if you're wondering whether ScyllaDB is actually the right fit for your workload, let's take a look at this chart. In fact, let's just cut to the chase here. And if you're already using DynamoDB and you have high volume throughput above, say, 50,000 operations per second, especially write-heavy workloads, and you want to achieve single-digit millisecond latency, then ScyllaDB is absolutely the right fit for you. It's guaranteed. So you can also see some of the other reasons there on screen why teams actually choose us. And one last slide before we get into it. What you're looking at here on screen is a snapshot of companies putting ScyllaDB to work in production. And what's interesting isn't just the big names, it's the diversity of use cases across the board. So we have different industries, different challenges, and one common thread is that they all needed a database that could handle speed, scale, and reliability without becoming a bottleneck. Okay, so let's revisit the agenda for today's webinar. Firstly, I'm going to be talking about why DynamoDB costs are often hard to predict. Between read-write capacity units, consistency levels, table classes, and auto-scaling quirks, there's a lot of moving parts that can affect your build in unexpected ways. Then we'll introduce our own DynamoDB cost calculator, and that's a tool that we've built to really give teams clearer visibility into the true cost drivers based on real workload patterns. And after that, we'll dig into some real-world workload analysis. Guy's then going to highlight some of the cost gotchas. He's going to talk about lesser-known things that trip people up and share sort of anonymous case studies from customers who've actually tackled these problems in production with DynamoDB and then have since switched to ScyllaDB. And finally, Guy will also wrap up with some takeaways and leave time for Q&A. So firstly, time for a quick round of speed dating. It's not that kind of speed dating. We're just going to test. I want to see how well you really know the DynamoDB pricing model. So feel free to just type your answers in chat or have a think about the answers. You don't have to reply to me, of course. It's a webinar. But let's go rapid fire through some of the key questions. And the first question is, do you actually know what the actual cost units are? So spoiler, if you're just thinking it's all about requests being billed by request for on demand, you're kind of on the right path, but you also got to think about read and write capacity units, and they behave very differently. They have different sort of conditions that we'll get into today. How much does a read cost compared to a write? Well, a write is actually 5 times more expensive than a read, just in terms of the list price. And I guess Mr. Bezos really needs to pay to fuel his rocket ship into low Earth orbit somehow. But if you're using strongly consistent reads or larger item size, then that gap can really narrow or even flip around. So you've got to be really careful here. How much more expensive are the different models? Well, on demand, if you didn't know, can be 3 to 7 times more expensive than provision with reserve capacity. And that also depends on, how flat your workload is and how aggressive your scaling is, for example, or how much you're actually reserving as well in advance. And this is where a lot of teams either overspend or really overcompensate trying to get the math right. And the point of this exercise is if you can't answer these questions quickly, you probably don't have, clear visibility into your DynamoDB cost model. And that's what we hope to fix today. So when most people think about database pricing, they assume that it's mostly about how much data that you're storing. But with DynamoDB, that's really only a small piece of the puzzle. And the real cost, of course, is shaped by how you actually access your data. And that includes whether you're doing things like reads or writes, if they're consistent or eventually consistent reads, for example, whether your traffic is sort of flat or spiky or a different shape throughout the day, and whether you're working, say with multiple AWS regions. These are all sort of cost factors that can come into how much you're going to pay. And in reality, most production workloads aren't that predictable. They tend to have traffic spikes, seasonal bursts, or even uneven access patterns within the day that can really throw off your cost expectations. So being asked to sort of forecast a year ahead is really tough when you're doing this stuff at scale. And while AWS does provide a pricing calculator, and I'll show you that shortly, it's really too simplistic for most use cases. It doesn't capture the sort of dynamic workloads or the caching layers or global replication overheads, for example, or even how auto scaling would actually behave under load. And that's the gap that we're here to explore today and why we built a better way to model this sort of behavior. Okay, so let me walk through a couple of examples that illustrate just how tricky it is to estimate DynamoDB costs accurately. And we can actually use AWS's own documentation to show you that. So we'll get over to the right screen. The first one is a developer guide, which is basically when to select different types of the pricing models. So what they have is, like I said before, they have two types of models, which is on-demand capacity and provision capacity modes. And they suggest that when you have a workload that looks like this, where it has a traffic pattern that evolves over time, or a variable volume of requests, or unpredictable request timing, or it's dropping to zero or near zero, outside of peak hours, then they suggest that this type of workload is actually good for an on-demand. But keep in mind that if you do pay per request in this model, like I said before, you're going to be paying 3 to 7 times more than you would if you were using a provision capacity mode. So this is their sort of suggestion here. And of course, you could try and estimate what this is. You could say, well, maybe I might take we might say that there's a baseline around the sort of 2.5 to 3,000 ops per second mark and try and accommodate these peaks. But it is a little bit difficult to sort of forecast what your actual spend is going to be, especially if that's changing on a day-to-day basis. And then they suggest that when you want to use a provision capacity mode is, of course, when you have more predictable sort of throughput. So they're saying steady, predictable, or cyclical traffic for a given hour or day, or limited short-term bursts of traffic, because there is a little bit of allowance that you can do there. And so what they're showing in this graph is a nice sine wave. I think it's got like two peaks. Maybe one is happening around 12, and the other one, I can't quite read that. I think it's at night around 6 p.m. So you got this sort of bimodal kind of pattern or sinusoidal pattern. And what this is, the orange is actually the consumed capacity, and the blue lines here are actually the provision capacity. So what's happening here is that they're using auto scaling to change the provisioning amounts of what you're paying for up front. And basically anything, you want to keep this blue line above the orange line, of course, because if you start to exceed that capacity, you're going to get request throttled. We'll talk about that. But all of this space here is basically dead or just wasted capacity. So capacity that you're paying for that you're not using, even if you're using auto scaling. So this is some of the examples why it's kind of hard to get it right. And then in terms of tooling, they have their own calculator, which if you haven't seen this before, I'd be surprised why you're even at this presentation. You definitely should check out their calculator. This is what it looks like. You just go in here, you can configure for DynamoDB. And similar to what I was showing you in the graphs, there's a couple of options here that you can specify at the table level. So you can say, I want to sort of configure for on-demand capacity, or I want to configure for provision capacity. Now, if you're brand new to this, just know that you can't have both on, of course. It's one or the other. But that's your options for input. And if we quickly look at on-demand capacity, we've got all the sort of standard stuff. We can chuck in some storage. I'll just chuck a light amount in. Noting that storage doesn't actually cost that much in comparison to some of these other costs, so we'll just minimize that for now. But when you're talking about on-demand capacity, you can start to enter things like how many, what types of writes you're doing, whether they're transactional or not. Now, keep in note that ScyllaDB doesn't do transactional writes, so we'll just ignore that part. But here you can specify the number of writes and also the number of reads in the next panel, basically by second or per minute or per hour, per day, per month, or per million per month. And I guess the way you would interpret that last chart is that you would need to figure out for all of the spikes, say, that happen throughout the day, those ops per second, you'd need to then, I don't know, chuck it into Excel, which we see a lot of customers do, and try and figure out perhaps what your total number of writes per day are and your total number of reads per day are to get sort of like an accurate figure. And so that's pretty much the way that you would estimate in using the AWS's own calculator. As you can see, it's a little bit limited. When you get into provision, you can do some additional things. So you can specify like a baseline rate, I should say, for both reads and writes. And now you're sort of limited to a per second view of the world. And then you can also specify what the peak is. And so the peak isn't attached to a particular hour of the day, it's just a width or a duration. So it's the number of hours per month. Once again, you would need to do something probably in Excel to try and figure out what inputs you use for that. And I keep mentioning Excel. We do see a lot of customers, actually using Excel to sort of come up with the costs themselves, because this calculator, let's face it, I feel like is a little lackluster. So let me switch back to the presentation. This is, I guess, where Guy and I have seen most teams failing at sort of accurately estimating costs. And the biggest challenge, of course, isn't just plugging in the numbers into that calculator. It's really about, converting a real world access pattern into something that the calculator can understand. And so if you need to take things like noisy, spiky, multi-dimensional traffic and then flatten it into a single number or two numbers like average reads or peak writes per second, that oversimplification can really hide the cost variability, and it often leads to bad surprises. So if you've been on the receiving end of that, obviously you can pay a really big bill if you get that wrong. And if you're a vendor or service provider, then you often need to align that pricing model with what your customers expect. So they might expect to be paying for storage, which is a pretty common thing for databases, but not realize that a surge in traffic across regions could really triple their bill overnight. So this mismatch between sort of real world behavior and the billing model is where most of the pain lies. And it's what we've aimed to fix with our own calculator and modeling approach. So that's why we've built our own version of the calculator. It's everything that I've just discussed so far about unpredictable workloads, overly simplistic calculations, difficulty sharing calculations, hidden cost drivers. All of these reasons really led us to build our own DynamoDB cost modeling tool. And the goal for me was simple. It was just to go beyond having static estimates and give teams the ability to model real life workloads. So there's also a stretch goal here, which we've yet to do. It's currently in the works, and that is to then apply our own ScyllaDB pricing to these workloads for comparison. But for now, we're starting with the fixed point or the known point, which is DynamoDB. And so you can access the calculator. The links are here on screen. It's just calculator.scylladb.com. I'm going to switch to these tabs just shortly to give you an idea of how it works. And then after I'm done with that, I will flip back to Guy for his part of the webinar. Okay, so let me go over here to this one. So this is the calculator itself. It's what it looks like. You can't see my query, my URL parameter bar, because I'm sort of I'm in full screen mode, but just if you open it yourself, you'll be able to see what I'm talking about. And really the concept is simple. I'm kind of like a visual person. I really like to see things in a graph. I think it's, obviously when you're talking about modeling workloads and then translating it back to costs, it's really good to be able to sort of see, touch and feel that sort of workload. And the way I've built this calculator It's a single page application. It's just using JavaScript. I think I've flicked past the code there. You can actually go and have a look at the code base. It's all open source. And you can see how I've built it. Most of the JavaScript and logic is in here. And I think in the calculator, for example, you can see all the functions that I use to do things. I'm not going to go through that, of course, because that would be insanely boring for a webinar. But this is the output of that GitHub repository. Feel free to fork it or send me pull requests or whatever you like. If you want see an error or you want to improve things or suggestions, definitely open for improvement. So this is what it looks like. And to sort of keep parity with the original AWS calculator, I have got this workload, which I call baseline and peak, and I've just put in brackets classic because that's basically the same types of inputs that you can enter in the AWS calculator. And the reason I did this one first was just to make sure that we have parity in the calculations, because I obviously want to make sure that this is accurate down to the nearest dollar. I don't show cents, but I can almost guarantee it's accurate to the cents as well. And just to give you an idea of what the type of workloads that ScyllaDB customers are running, what it might cost them per month. So in baseline and peak, you can enter your, as it suggests, you can enter your baseline reads and baseline writes, and you can also specify what your peak reads and writes are just with sliders. You can also type things in manually if you want. You can move things around and you can see things moving on the chart, etc. So it's all nice and hunky-dory there. You can enter all of those inputs. And like I said, if you see in the URL parameter, which you can't see on my full screen mode, you can also change those inputs as well. And that becomes important when you want to start sharing this calculator, perhaps with your boss or with your colleagues, as to how much a particular configuration costs. So that I had that in mind in terms of when I was building it, to also make it really easy to share. Now you can control in classic mode the duration of those peaks. So just once again, it's not set to the hour of the day, even though you can see the hours at the bottom. I'll talk about that in a second. But this just lets you change the width of how long that peak lasts for. And you can also change the operation size. So this is a really big cost multiplier that Guy will no doubt get into. But the basics are that writes are rounded up to the nearest kilobyte and reads are rounded up to the nearest 4 kilobytes. So this has a really big impact on cost. So if I start to put like a 55 kilobyte payload through there, it's obviously going to cost me, well, more than a rocket ship to the moon, I think. Well, at least one way anyway. It costs a lot of money, so definitely that's a big cost driver. You can also experiment with read consistency. So that's basically one of the units that we were talking about before in terms of how many read units you use. Is governed by, in part governed by the consistency of those reads. So how many trips it needs to make, and that's it for the sort of baseline classic. You can flick between provisioned and capacity modes. Provisioned, obviously the costs start to come down. So if we have a quick look back here, we're at $10 million a year, and if we switch to provision, we're down to 3 million. So there's that sort of 3x improvement. And remember before I said it can be like 7 times cheaper. That's based on if you start to reserve capacity up front. So you probably know this already, but if you're willing to pay up front, and this is all set to like a 1-year reservation, then you can drop your annual cost further with an upfront cost. So you pay a chunk of money up front, and then and so that's really asking you, I'm really sure about this capacity over the next year or 3-year term, whatever you sort of choose. Obviously 3 years would get a bit cheaper as well. But the calculator is working on the premise that most people are reserving capacity, sort of on a year time frame. Now, a couple of other things that are a little bit different that compared to, say, the AWS calculator, we've got this thing called over provision capacity. And the reason I put over provisioned in there, because if the solid orange line was my actual write workload, obviously if I only provisioned the actual, what I'm consuming, there's a really high risk that, if my forecast is wrong, I might consume a little bit more than what I provisioned throughout the course of the day. And as you start to consume more than your provision capacity, then there's an artificial limit that DynamoDB places on you, which is, of course, called request throttling. And basically what that's going to do is reject requests that you're making that are exceeding your provision capacity. And that's going to be terrible for your P99 latency, because it's not even like a slow request. It's like a failed request. Okay, so and then you have to put application retries and all that sort of stuff into your logic. So that's terrible. So what we want to do, just to make it a bit easier, because most people do this if they're doing the spreadsheet way, is just add a little buffer. Now that I suggest, 20% buffer. It's really how comfortable you are around, knowing what your workload profile is. So that's an additional thing in the provision. I've spoken about read and write reserve capacity. There's some other things in here as well. There's the ability to factor in global multi-region global storage, or global tables, I should say. And so this is basically starting to increase the number of, let's say we call them data centers in ScyllaDB. So how many data centers you want to replicate to. This is going to have a big impact on costs. Guy is going to talk about that. He's also going to talk about DAX or caching in here, but you can plan for this. There's stuff in here which will calculate, do some maths for you, and make some recommendations on what, based on the sort of cache set size, and also the hit miss ratio of your cache performance. It will make some recommendations on basically how many DAX nodes it thinks you need. But if you know better, you can also change the number of nodes and what type of nodes that you want to reserve for DAX as well. So that's all cool stuff. Guy's going to go through this in more detail. The main thing I wanted to show you, or before I hand over back to Guy, is I added all these other modes as well. So instead of the baseline and peak, which is just classic kind of boring, I wanted to get into more like what's a realistic workload. So we were talking about those workloads before, and saying that it's really difficult to model. Well, with this tool, you can actually go in and start with a preset, and then go and customize things if you like, for actual different types of models. So maybe you have different peaks throughout the day. Maybe it's just a business hour where you had the morning peak and the afternoon peak, and maybe you have some overnight batch processing, or maybe your writes go through the roof. So you can and you do that all the way until whatever it is, like let's just say 2 a.m. while you have that batch process. So you can go and control all of this individually. You can also control those series in the URL bar as well. So if you don't want to be dragging little handles, and that's going to dynamically update your prices. It's a really good way of doing things. The only other thing I want to sort of say here is in the AWS calculator, it's a bit cheeky, but when you set the reserve capacity on reads and writes, if you notice the fine print, they just say that you will only reserve up to the baseline capacity, say 80% of your baseline, for example. But what I found a lot of customers are doing is that they want to reserve somewhere up to their peak. And so that's what these real life workload models let you do. They can let you drag anywhere up, sorry, not the over provision, wrong slider. They can let you drag up to the peak of your capacity if you want. And if you look at the bottom cost in terms of, let's look at total annual upfront costs, and I'll just sort of simplify things just to make it a bit easier to work with. What you'll see here is, as you start to drag the slider, things are going to get cheaper over the course of the year. So we're getting down to 4 million, getting down to 3 million. But you see there that this sort of like little inflection point where things start to get expensive again. And that's because you're over provisioning. So this tool is actually pretty cool for just finding what's a sweet spot in terms of reserving up to your peak capacity. Obviously, you don't want to reserve all of your peak because you'd be paying too much, but you can start to find those inflection points. And I think that's enough of me talking. I'm coming up to about 20 minutes, I think, so far. So I'm going to get Guy to basically get ready with his part of the presentation. He's going to start talking about slide gotchas. So feel free, Guy, at any stage to take over, and we'll catch you at the end.
Thank you, Tim. Working with customers means that we see all sorts of situations, especially the one that will help them in cases where they had little anticipation to what come next. So while DynamoDB is really easy to get started, several aspects of cost can usually get users off guard. Here are some examples of those situations. Let's start by the item size, or the payload size in bytes, specifically in the context of an item, which is a major cost driver for DynamoDB. Doing 1 million writes per second at 100 bytes costs majorly different than doing so at the 5 kilobyte mark. However, there's a gotcha. As the cost is measured in kilobytes, whenever you cross the measurement threshold, you'll be paying for the next cost level. For reads, that means that every unit that is charged at 4 kilobyte will also be, assuming for consistent reads, or 8 kilobyte for eventually consistent reads. Now let's assume a consistent read where if you were to read an item of 4.5 kilobyte, you would pay for the next leg up in pricing, effectively wasting 3.5 kilobytes of that unit that you paid for. The operations are also class dependent, so the cost varies depending on which class the table is deployed on and which consistency level you imply on that operation. The same will happen to write, albeit to a higher granularity. The writes are measured in kilobytes, so for every kilobyte in a write, it consumes a write unit. So let's say an item size crosses the kilobyte threshold, let's say 1.2 kilobyte, you pay for actually 2 write units, wasting 0.8 units in that case. The write cost also varies per table class, so it's something that really you should keep in mind when you're starting data, especially for the long term. Last but not least, the item size are limited to 400 kilobytes. This is not tangential to cost, but it's still a good number to keep in mind as you plan your application design. You don't want your power users to discover that they can't add any more tags into your inventory just because you didn't anticipate this limit beforehand. Our calculator actually helps understand cost at various item sizes. So it doesn't account for some gotchas, such as the conflict resolution write costs, especially when parallel writes to an item are submitted between different regions, and those writes arrive at DynamoDB. They will be conflict resolved by DynamoDB conflict resolution algorithm, but they'll still be accounted for separately, even if only one of them finally applies to the base table. And also, as you're manually doing TTL or expiring data or deleting data, where those cases where you rely heavily on application logic to expire data, you might also incur high costs just by reading lots of data, transferring them to the application, and then deciding which items to delete. Even when you're just using scans that return multiple items, which is a good practice, and might be good to round up those units depending on the average item size, it will still consume a vast amount of units. Then, when you issue a delete, the units associated with that operation are considered based on the size of the item being deleted. So even if you're just submitting a delete request with the headers, with the keys that you're deleting for that specific item, the whole item size is accounted to measure how many operations, how many units that operation incurs. Even though your scanning and deleting might sound like a lightweight operation, it still can be extremely cost prohibitive. Global tables are also a great way to ensure high availability of your application's data and your application functionality. It's used to replicate data in an active-to-active manner to regions dispersed across the globe. And let's assume that you have a video streaming service that uses Dynamo for storing the play state of your customers. You don't want those customers to lose their last viewed state as they step out of a plane on another continent. That's exactly how global tables work. They provide local access at low latency to data that was originally written in another region. That data is enqueued, those writes are enqueued and distributed them to replicas on the base table. However, there are surprising aspects to its usage. First, every write that is accounted for the base table or the initial region that the write was sent to, as well as the replica. So that means that all writes are multiplied by the number of regions by the size of the payload, which the item sizes also affect the write unit consumption for every region. So let's say you write a 3.5 kilobyte item and then replicating it to 4 regions. You end up paying for 4 times the number of units that you'll be paying for a single region, and you're also effectively wasting half a kilobyte unit because you're replicating it outwards. On top of the actual payload size, you also pay for the network transfer for every replicated region at cross-region prices. So effectively, the cost is much higher than just the base table write and the replicated cost. So assume that you do billions of writes per day. Depending on the payload size, it might be an astronomical amount just for this workload. Our calculator helps by allowing you to experiment with different settings, such as the regions of global table, the payload size, and we automatically calculate the replicated write cost as well as the associated network cost for the replication. You get a complete view of all aspects of the global table workload, which allows you to understand where costs come from and possibly where to mitigate them. However, the calculator doesn't account for some situations where it might be a good idea to review on your modeling, such as items written to multiple regions in parallel will be replicated and their unit costs computed, but the last end state will be a single item that has its conflict solved by last write wins. So you'll be paying multiple times over because you're replicating data, but only a single version of the item will live. We also assume that all pricing to be US-1 for ease of consumption, but regions have varying prices for units and for network. So look closer, especially in those use cases where you're running on premium priced regions. DynamoDB tail latency is known for being on the higher side, so it's not uncommon for our users to see over 2 digits millisecond latency, especially for reads P99. When improving latency, the DynamoDB Accelerator, aka DAX, is used to improve the read latency of latency-sensitive workloads. Although it really helps with latency, it also introduces a large cost and management overhead. You need to pick the right number of nodes to form the cluster and tune it according to the result of that for your workload. Others prefer to run their own solution to tame costs, such as running an elastic cache layer or even their self-managed Redis cluster. The cost usually is lower in those situations, but they introduce challenges. You now have to manage the cluster yourself, as well as handling cache replication and invalidation on the application side. How do you handle a case where either the base table or the cache update fails? Your application needs to account for all those corner cases. Our calculator helps you reason about the cache in a different way. It starts from the base table size, the average throughput and cache hit ratio, and then it deducts the cost from the perceived hit ratio. Read units are effectively reduced as reads from the cache are considered free if they're done on the same AZ or availability zone. Otherwise, they might also include network data transfer costs. However, some things to keep in mind are the cache warm-up cost. As you scale your DEX cluster, it takes a while to catch up, especially with those incoming reads and cache misses, effectively using read units in that period and also elevating your overall latency. The goal of the calculator is not to allow for an immediate latency versus cost comparison, but gives you tools to weigh them and decide which is the best approach depending on your workload characteristics. It also does not infer any potential savings depending on the cache method that is chosen, but keep in mind that DAX instances are built at flat hourly rates, so usually means you can't reserve them to leverage a more advantaged price strategy. So we discussed some details on the calculator's implementation and some price gotchas that got some customers surprised. Now let's look at some real-life use cases under the calculator's microscope. Let's start with the first use case, which is a recommendation engine for a streaming service. The streaming service serves those recommendations to unique user profiles across any region they operate. These recommendations are generated daily and written to the database in large write operations. The database also holds user preferences, such as ratings, and can be written from any regions as the user migrate. The profiles are also tailored to each user's preferences in their watch history, which increases user retention and engagement on the platform. As a streaming user who's traveling abroad, you want to continue watching exactly where you left off on your previous location. This information is quickly fetched from the nearest region, ensuring minimal latency, especially when using the service anywhere on the globe. There are a total of 6 regions distributed across continents. So as users interact with the service, they generate feedback information that is written to the database, always at the nearest location for minimal network latency. So when a title is paused or is completed watching, its state is stored in the database as well. As titles or new titles become available and gain different priorities within the recommendation pipeline, those machine learning algorithms generate user-specific recommendations on a daily basis. This increases the time viewers stay on the platform as they continuously engage with the content that is highly relevant to their interests. This specific workload is composed of these metrics. So it's a 1 petabyte table spanning 6 regions. It follows the DynamoDB recommended single table design where all recommendations as well as user-generated feedback is stored on the same table. The table size starts at 1 petabyte, but it also replicates to another 5 regions. So the overall table size grows according to the number of regions. The average item size is 10 kilobytes. Some items are a little larger than others, but we'll use the average for an estimation. This item includes a machine learning generated recommendation list, user feedback, and user metrics. Reads baseline is 100K operations per second, and it peaks at 500K operations per second for 10 hours a day. So it goes from 100K to 500,000 operations per second for 10 hours. The write baseline is 400K, peaking at 1.2 million for 12 hours a day. That peak is caused by the daily batch load of recommendations, where new recommendations are written for every profile. These writes are done on a single region and replicated across all the other regions through the global tables replication. As users interact with the service, the updates they generate are sent to the nearest location and then are replicated to the other regions. Here we can see the batch write operation, which take over 10 hours to complete. So all user profiles are regenerated and inserted to the database daily. So most items are being touched on that update. On the right-hand side, you see the sine wave of users on their daytime per region and the drop during the evening and early morning. We can see small-ish spikes as some unpredictable events happened and drove the reads to increase in a burst. So this is obviously a very large and complex use case. Let's break down by some of the challenges they saw. As they used a single table approach, they had users' watch history, feedback, and preferences all stored alongside recommendations. This means that everything the user does generates writes that are then replicated across all existing regions. These replicated writes, as long as with the base table use case for recommendations, increase the cost by a very large extent. They used the provision capacity to deploy the table, so this also meant that they could tune the capacity to handle higher traffic period. However, they had issues while serving requests during unpredictable traffic spikes, such as when a title was recommended by a celebrity on social media. They also had to manage the table capacity in preparation for global launch events. Titles were very highly anticipated, generated a burst of interest on the platform. So in order for the table to be ready, they had to initiate a scaling of the provisioned resources hours before the launch and make sure that the table was ready and usually over-provisioned to take in that new spike in workload. The tail latency is also a major concern. They saw very frequently high tail latencies for reads on the PIN line, but due to the size of the data set and the low cache hit ratio, they were unable to cost-effectively use caching mechanisms to serve those reads. So if a user were to move out of AWS, they would not be able to do so. Using Dynamo via public communications or VPN or any sort of remote connectivity, although it is possible, it adds a ton of latency and cost to an already massively expensive use case. And of course, this all boils down to cost. Even though reads are quickly served from each region, every write operation has cost overhead for any operations. So let's think about the cost drivers that we just discussed. First, running on demand is easy. It's possible, but the table can handle spikes in operations pretty seamlessly And the team doesn't have to think about the cost, but it has the major cost overhead. So they don't have to plan for it. They just have to pay a high price tag alongside it. The 6 total regions for global table also means that a major cost hit caused by all writes incoming from that daily user recommendation generation and also from the user activity. Loading the table daily also has massive cost overhead. In cases where those recommendations didn't change between days, the application still writes it to the table and consume write units. If they were able to use conditional writes, the same would still happen, as those writes with failed condition still consume write units. So using the calculator to take a closer look, we see that the daily peak of writes, essential to keep those recommendations up to date with the desired state of the service. On the left-hand side, we assume only the incoming reads and writes. The overall cost for that use case with all regions, but without the peak load, is $112 million per year. If, on the other hand, on the right-hand side, we include the peak caused by spikes in writes and reads on top of the base workload, it jumps to $221 million per year. It is already sometimes the whole revenue a use case might bring to a company. So using the calculator allows us to easily simulate multiple scenarios, understand the costs associated with them, and follow up on how to tame costs. And speaking of which, our calculator helped the team understand the cost drivers for the use case, even when they admitted that there were very little optimizations they could apply. After all, they needed all regions to serve traffic locally with low latency, and the item size was not flexible, as the number of titles included on the recommendations was not really something they could change. The cost of running the workload far surpassed the cost expectations, and growth was underway with more partnerships and titles joining their catalog. So, what were them to do? This team tried CLDB out and really liked the technology. Beyond being just a global scale database, it also offered predictable low latency for reads and writes. CLDB's model is capacity based rather than operation based, so it is much more efficient for pricing. CLDB also offered tons of improvements for the workload, such as network compression, which reduces inter-availability zones and inter-region network costs. Compression for data on disk, which reduces the overall storage footprint for that massive 1 petabyte data set. And it efficiently allowed them to run much faster, especially their daily batch, with a significant decrease in runtime, so it processed faster. CLDB also allowed them to run anywhere, so if they were ever to migrate to another cloud provider, or even run on their own on-premises hardware, they were free to do so. Their cost was reduced to a fraction of their current bill, so CLDB's predictable capacity-based pricing and built-in efficiency optimizations, now they have both better performance, much lower total cost of ownership. This allowed them to scale their business confidently without worrying about unpredictable spikes, both in their latencies and database cost. So now let's look at another use case, how a NetTech company leveraged caching to hit their latest targets, accompanied by a cost shock story. In this scenario, the team used DynamoDB to serve ads and real-time analytics for multiple regions on their service. They used a global table to ingest all their data to serve billions of requests a day on each region. The baseline for 4,000 reads per second reached 105 reads per second, 105,000 reads per second for 4 hours per week, their busiest time in each region. Their spike was caused by our analytics pipeline that saturated their provision capacity of the table really quickly. And they also tried to leverage outscaling on the table, but it didn't react fast enough. And the table performance really tanked with analytics queries draining resources from the live user workload. Writes saw a steady flow of 6,000 writes per second, peaking over a little over 3,000 writes per second. 30,000 writes per second, sorry. The writes baseline is usually generated by expiring offers and other metadata adjustments. Their peak is generated by mostly ingesting new offers. Each item in this case is fairly small, so just 246 bytes on average. So if you remember we just discussed, write units in Dynamo are measured in 1 kilobyte increments. So this means that the writes effectively wasted 75% of the units they consumed and paid for. So the overall data set was 1.1 terabyte, comprised of a couple of tables that were required by the application, all of them deployed globally. And they replicated the data using global tables, so total of 4 regions for local access of the data. In order to achieve the desired latency for their workloads, the team then deployed DAX, which is a very common solution. As they used multiple tables and had multiple workloads, each one of them had to deploy a DAX cluster separately to reach their latency goal. For their use case, user ID store, they needed to deploy larger nodes so they would reach a higher cache hit ratio to sustain their latencies. Each workload had different profiles for each region, so the DAX cluster looked different for each of the regions. And overall, the team deployed 48 nodes of varying sizes across all their 4 regions. In this example, we use the calculator to understand the difference between over-provisioned table to handle the spikes, but still have unpredictable latency, which was not acceptable, versus leveraging DAX to a large deployment to ensure their cache hit rate was sufficient for their latencies. You can use the calculator to explore different levels of cache utilization for your workload and assess the cost impact of those deployments. For this case, the overall deployment was a little over 400K for a year, including DAX. Now, I bet you're wondering how this team solved this issue. They can't live without a cache, as latencies will climb to unacceptable levels, they'll lose revenue, and they can't continue to add cache because the cost has already skyrocketed. So this team also evaluated ScyllaDB for their use case, and Scylla was chosen to help them to reduce cost. ScyllaDB's efficient built-in cache leverages the computer's instance memory for storing rows that were recently accessed. It automatically manages space by evicting rows that were not used for a while, making room for a recently accessed piece of data. As it uses the instance memory, there's no additional cost. It's just part of the ScyllaDB's design to make extremely efficient use of compute resources. They also use workload prioritization and advanced features for analytics. Workload prioritization is a ScyllaDB unique feature that allows them applications to run with different performance characteristics to run alongside each other without hurting performance. These allow their analytics workload to run in parallel with their online processing without polluting their cache or hurting their latencies. They also use TTL for volatile data, so those user sessions that were short-lived had to be deleted from Dynamo, increasing the cost of writes. So they looked into ScyllaDB, they designed their tables to store user sessions and automatically invalidate them after a given period of time. This helped curtail the storage growth. At the same time, immediately invalidated sessions as soon as the TTL was reached. ScyllaDB cost model is more advantageous than Dynamo's. So as users pay for the cluster capacity where all features are included, they can utilize the cluster to its maximum extent. ScyllaDB also ensures price competitiveness, reducing 50% of your DynamoDB costs guaranteed. So here are some key takeaways for these use cases. DynamoDB costs are nonlinear and they're really pattern dependent. So it really depends on how you're using Dynamo, not what is just your base use case metrics. There are many cost amplifiers to Dynamo. So if you are running on Dynamo and you have cost issues, or if you're planning to move to Dynamo, you should really look into the fine print and look at those amplifiers and estimate them for your workload in order to avoid those price gotchas. The native calculators really miss real-world burst and load nuances, and really, this is really what captures most of the cases that run away with predictable pricing. And you can use our calculators to anticipate those spikes, how would costs look like under those deployments, test your caching or global strategy cost, how your application will drive those specific metrics, and overall to avoid surprise bills. So really, we do have a couple of questions now, Tim. And I'll start by taking the first one. So the first one is, what do you mean by 50% of DynamoDB price or cost in general? So ScyllaDB is able to be really efficient in terms of cost and to pricing, price performance by leveraging shard per core, which is a feature of is exclusive to ScyllaDB that allows it to scale linearly for each core that is added on the cluster. It also works closer to the hardware, so it really manages the hardware to its fuller extent, delivering all the capacity that the hardware can, and also has efficient built-in cache. So whenever you're running Scylla, apart from its efficiency from the ground up, it also has built-in cache. So you don't need to think about adding another cache layer on top of your database. There is no paper table or paper requests. It's all capacity based. So whatever your cluster can process, you still can incur on that cluster without any additional cost. Okay, so Tim, would you like to take the second question?
Yeah, I think it's along those lines of how can ScyllaDB help reduce the costs, and it's kind of to follow what Guy said. A lot of it is taking advantage of modern hardware. So we spoke about shard per core, use of NVMe storage. But that just drives a lot of efficiency, essentially. In terms of network, there's really good compression. In terms of like compared to DynamoDB, where you're used to sort of paying per request and then getting throttled if you get that wrong in terms of provisioning. ScyllaDB, you're really paying for compute and storage. And so that gives you a lot more leeway in terms of how your resources are provisioned. I think it's true to say that, in all use cases, you tend to over provision, but the difference with ScyllaDB is that you get more sort of a buffer, I guess, some burst performance that you can, if things went wrong and you had that little spike at 12 p.m. daily that you didn't really forecast, but is happening now, well, ScyllaDB will be able to sort of soak up those additional requests. You're not going to get charged like per request. I think there's some other things as well, like Guy mentioned, workload prioritization, consolidating multiple tables into your cluster. It takes away all of that headache. And so that's a cost reduction as well. And probably, the last thing, which I'm sure there might be more questions on, is just around elastic scaling and how we, especially with tablets, how we can sort of dynamically allocate data across the cluster. These offer like enormous benefits in terms of cluster capacity and getting closer to higher utilization of the resources that you're paying for.
Amazing. I have a third question, which is having multiple workloads online in analytics, how can I make efficient use of a cluster that hosts those many workloads? And ScyllaDB's workload prioritization, which I believe Free touched during the presentation, is really aimed towards allowing you to run multiple workloads on the same cluster with different priorities between them and allow them to fully utilize the cluster capacity to its maximum extent while they're still processing within their acceptable latency ranges. So that's really something that you should look into. Would you like to take a final question, Tim?
Yeah, I think the last one is how can ScyllaDB Cloud be more efficient? That's a good question. I think the ScyllaDB core product is the same, whether it's enterprise or cloud, just to dispel any myth there. But obviously with cloud, there's a lot, just in the way that your team operates, there's a lot of stuff that you don't have to now manage. You don't need a full-time ScyllaDB person. You're kind of getting that as part of the database as a service. So aside from the obvious, being a managed service and running in the cloud takes away a lot of that sort of administration overhead. There's other really nice features on cloud as well. And so that's probably a good segue actually into our next slide. Do we have one on xCloud? Guy? Yeah, but so ScyllaDB xCloud has been recently launched. So that's taking advantage of things like tablets that I mentioned, clusters that can be resized automatically to achieve much higher efficiency in terms of storage utilization, as high as 90% storage utilization of your instances. So that's something definitely worth checking out. Go check out the links on our main website at scylladb.com.
Amazing. Thank you, Tim. So yeah, as Steve mentioned, go to cloud.cladb.com and start a free trial to play with the platform, familiarize yourself, and really use the latest cloud release to allows fast scaling and multiple maximum efficiency, although while reducing cost. So we really invite you to try our calculator. The link's on the screen and also on the chat. So tell us, what else would you like to see in a calculator? Are there specifics you'd like to see and compare? Did we miss anything? You really should get in touch if you need help with modeling or understanding your workload. If there's anything that you'd like to discuss, or maybe to theorize how can you improve your cost, reach out to us. And of course, thank you for joining today.